Hi guys, Mr. Janowski here. This is the third part of the Chapter 13 slide videos. In the last part, we learned the difference between luminosity and brightness. In this one, we're going to learn a new idea called the Stefan-Boltzmann law, and then put this idea together with the old ideas and see how astronomers actually use them to do interesting, important things in astronomy. So let's get started with that. So, quick review. What is the difference between luminosity and brightness? In plain English, they kind of mean the same thing, but in astronomy, they have separate meanings. In astronomy, luminosity is how bright the object actually is, and brightness is how bright it appears to you. So if we're looking at all of these lights, all these street lamps here, these guys all have the same luminosity. The bulbs are all basically identical. They're all putting out the same amount of light, so we say they all have the same luminosity. They're all equally luminous. However, the streetlights that you're closest to, you would say these are brighter because they look brighter to you. So where this photographer was standing, this is the brightest bulb. If there were another photographer down here closer to the arch, that photographer would say that, these are the brightest bulbs. So it's important to understand the difference between these two. Know the difference between them. And the second question, what formula relates brightness, luminosity, and distance? This is called the inverse square law. So B, brightness, equals L, luminosity, divided by 4 pi d squared, where d is your distance from the light source. It's called the inverse square law because brightness varies according to the inverse of distance squared. So the distance you are away is in the denominator, and it gets squared. So it's an inverse square law. Physicists love inverse square laws, by the way. So, if you had two stars and they were the same temperature, how could one be more luminous than the other? So, think about that. How could that be? If you were closer to one of the stars, would that make that star more luminous? No, that might make that star brighter, but it wouldn't make it more luminous. Remember, luminosity has nothing to do with how far away you, the observer, are from the thing. Luminosity is how bright the thing is, in and of itself. So, what would make two stars that were the same temperature? What would make one of them more luminous? One star would be more luminous if it were bigger. So here we've got two stars that are the same temperature, as indicated by they're both the same color of orange. And yet you see more lines coming off this one at the bottom. Well, it's bigger. It's got a bigger surface area, so it's putting out more light. Slightly different question. If you had two stars that were the same size, how could one be more luminous than the other? And the answer to that is one of the stars could be hotter than the other. So it's a little hard to tell in this picture, but imagine that this star is the same exact size as this star. But this one's, it's glowing hot blue. This one is much brighter, and it's putting out more light, which, again, in these pictures, it's indicated by the fact that there are many more lines coming off of this one. So there's a Kahoot. If you have two devices, you can play the Kahoot by yourself. Start the Kahoot on your computer and then answer the Kahoot questions on your phone if you want to. Maybe you can find some clever way of playing the same Kahoot with somebody else in the age of social distancing. But yeah, there's a Kahoot. Give it a whirl. So this new idea, the Stefan-Boltzmann law. This law relates an object's luminosity to its radius and its temperature. So L equals 4 pi r squared times this. This is the Stefan-Boltzmann constant. This is actually lowercase Greek letter sigma. Looks nothing like a capital sigma. Times temperature to the fourth power. So this law, it looks like a mess. It's very intimidating. There's a lot going on, and we've even got this weird little Greek letter here. If you actually break it down piece by piece, it's not so bad. L for luminosity, so the total energy radiated per second by the star, the star as a whole. This depends on the total surface area of the star. So these are like the two questions in the do now. If one of the stars is bigger than the other one, it's going to tend to put out more light. It's going to tend to be more luminous. And the other thing is the amount of light it puts off is dependent on its temperature. And it's actually dependent on its temperature to a very severe degree. So this is, the constant. That number is not going to change, but it varies. Luminosity varies, has temperature to the fourth power, which means if the temperature goes up by a little bit and you raise that little bit to the fourth power, it means your luminosity is probably going to go up by a lot. So how do we actually use this idea? So let's say we looked at the star Sirius. Oh yeah, I wish I were there in person to point this out to you. So yeah, how can you see Sirius? If you look at the stars in Orion's belt, they make a line that points almost directly to Sirius. I don't know, useful little thing to do. So astronomers looked at Sirius. They analyzed the light coming from it. They figured out, well, what's my maximum wavelength? They plugged it into Wien's law, and they figured out that Sirius has a temperature of about 10,000 Kelvin. So Sirius is hotter than the sun. The sun is about 5,800 Kelvin. So after they did that, they then measured its brightness using photometry, basically a light meter. They looked and they said, well, how bright does this thing look to us? So they measured its brightness that way. And then Sirius is close enough that we can actually measure its distance from us using parallax. So we did that, figured out its distance. Again, we measured B with photometry, its distance D using parallax, and then we plugged it into this formula, and we found the luminosity of Sirius. And it turns out that Sirius is about 25 times as luminous as the sun. So if you were the same distance away from Sirius as the Earth is from the sun, it would look 25 times brighter. So yeah, a lot of math here. This is what we in physics call a ratio problem. We're not actually going to do this whole thing. But yeah, here's the key idea. You can take those things that we just figured out, the luminosity, the temperature, compare it to the luminosity and the temperature of Sirius, and compare it to the temperature of the sun, plug all that into Stefan Boltzmann's law, do a bunch of algebra, and at the end, you're going to find out that Sirius has a radius of about 1.6 times the radius of the sun. So yeah, it's bigger than the sun, but it's not hugely bigger. It's not even twice as big as the sun in terms of radius. It's only 1.68 times the size of the sun. So if it's only 1.68 times as big as the sun, why is it 25 times more luminous? Because it's much hotter. So remember, we figured out using Wien's law what its temperature was. The temperature is not quite twice the temperature of the sun, but remember, in this formula, you're going to take the temperature to the fourth power. So yeah, that's how that works. So all of this stuff, we used Wien's law, the inverse square law, and the Stefan Boltzmann law to figure out the radius of Sirius, at least how the radius compared to the sun. There is another way to do it sometimes. So you can actually, in very rare cases, really directly measure the radius of the star. So this only works with stars that are like Betelgeuse, which is enormous, much bigger than the sun is, and it happens to be very close. So yeah, you can actually measure it kind of directly. Just point your telescope at it and measure it. So how do we do that? So the first one out of these three images, the first one, this was an image of Betelgeuse taken with the Hubble telescope. So the Hubble telescope, of course, is limited by diffraction, as all telescopes are. And remember, you get this kind of pattern. Quick, what's this kind of pattern called? It's called an Airy disk. Yeah, it's a diffraction thing. So Hubble's limited by diffraction, so it couldn't resolve Betelgeuse any better than this. It's basically just a big blurry thing. So this second image, this was taken with this weird, this is called computational photography or computational astrophotography, in this case called speckle interferometry. So not a regular interferometer like we're used to dealing with. This is a neat technique. You can do this if the star is very bright. You just rapidly take a bunch of really quick photos of it and then get a computer to compare those photos. And any one of the individual photos will be pretty poor. But by taking a whole bunch of them and then comparing them rapidly, you can get a pretty good image of what the actual thing looks like. So this is called computational photography or astrophotography. In this case, your phone actually knows how to do this trick too. And then the last way, how do we get the sharpest one? Well, we just use the good old-fashioned interferometer. So remember, if you have an interferometer, you can get around the diffraction limit. Well, you can't get around it completely, but you can do better with diffraction. By placing your telescopes very far away, you can measure very small angles. So, yeah, this is an image of Betelgeuse taken with a ground-based interferometer. So here are the three pictures again, just so you can quickly compare them. So when we measure the radiuses of stars, either by that first way, the way we did it for Sirius, or sometimes, with the direct measurement thing, and you find all the different sizes of stars, you'll find that most stars are actually pretty close to the sun in their size, and we call them dwarfs. There's basically only two broad classes of stars. Stars are either going to be dwarfs or they're going to be giants. It does get a little more complicated after that. There are supergiants and hypergiants and things like that. But yeah, for now, let's just say all stars are either dwarfs or they're giants. So most stars are actually pretty close in size to the sun, within about an order of magnitude. A factor of 10 bigger or a factor of 10 smaller, pretty close to the size of the sun. But some, like Betelgeuse, are way, way bigger than the sun, and we call those stars giants. So this is a very binary way of looking at it. You see a star, you figure out its radius, and you put it in one of two groups. It's either a dwarf or it's a giant. So there was a quiz on Google Classroom due next class. Not really. There are quizzes on Google Classroom. You can take them. They're ungraded, just if you're keeping up with this stuff, just to check your knowledge of it. So yeah, it's already actually up there on Google Classroom. So to quick review, what law lets you determine the temperature of a star by observing its light? So this is an oldie but a goodie. We've been doing this one for several chapters now. This is Wien's law. So look at the light. So let's just look at this red one here. So this would be the light from Betelgeuse. Figure out at what wavelength is Betelgeuse putting out the most light. Plug that wavelength into this formula, and it gives you the temperature. So Wien's law, very useful. What is the formula that relates brightness, luminosity, and distance? That is the inverse square law. So B equals L over 4 pi d squared. So both of those ideas we learned in the previous part of the slides. This is the idea from this one. What's the law that relates luminosity, radius, and temperature? That one is called the Stefan-Boltzmann law. So luminosity equals 4 pi r squared, where r is the radius of the star, times this sigma, which is the constant, it's the Stefan-Boltzmann constant, times the temperature to the fourth. So again, if we're looking at the math, we would say that luminosity has a very strong dependence on temperature, meaning if the temperature goes up by a little bit and that little bit gets taken to the fourth power, turns out the luminosity is going to go up by a lot. And that's it for this part of the slides. So hopefully you're finding this helpful.